Okay, so I hope this shows up well. This is our 4D permutahedron, and it projects down into 3 space. And can you tell me a little bit just about the shape?
So like the other one, you take a set of numbers, but this time it's 1, 2, 3, and 4, and you permute them into different orbits, and it makes this shape. And to find which, because this is a 4-dimensional shape, to find which vertices are which, like we labeled them all. So we labeled 1 as 1, 2, 3, 4. Not sure where it is, and then to get from one vertice to another, you have to switch 2 numbers that are 1 away from each other. Like you could switch 1 or 2, for example, to get to this, 2 or 3 to go over here, or 3 to 4, 3 and 4 to get down here. But
Okay,
this
nice.
might not be the actual ones.
Yeah, that's okay. That's how we make it. So can you tell me some things about the actual shape we have here, made by the green struts?
The shape we got is a truncated octahedron. So it's or the intersection of an octahedron and a cube, kind of. You see the cube around it, and then the octahedron gets chopped off at these squares.
Mm-hmm.
It's got some symmetry. It's got some similarities to the hexagon we had before.
Okay, what are those? Actually, that's an interesting comment. What are some similarities with the hexagon we had before?
We have hexagons. We have some groups of 6, kind of going around like in these rings. There's a few groups of 6, just depending on how you look at it.
Where point to 6 balls that you're talking about.
Oh wait, no. That's kind of 8 if we look at it that way. But I think if we turn it, I don't know how well this is going to show up, but if you turn it on a hexagon, you can see like there's like a group of 6 going around the bottom. There's a group of 6 going around on the top end of these squares. There's another group of 6 going up here.
There's the
There's
top.
a final group of 6.
Okay. Can you see a group of 6 with it arranged like this at all anywhere?
Let's see. So I think if you rotate it a certain way, all of the vertices that have 1 as their x or their beginning coordinate would be on one hexagon, and then like it would go because there are 4 layers. Like if we had this hexagon facing the bottom, there would be 4 layers of 6.
Okay.
So.
Interesting. All right. Now we can set it down, like you said, in 3 dimensions, like this, with a hexagon at the bottom, or we can set it down with a square at the bottom.
Yep.
Now, your brother and I were studying this for a different reason yesterday, and we found that when the square's at the bottom like this, there's a real amazing surprise, which was what?
Which is that the surprise was basically this, that all the coordinates lie on integer, in 3 space on integer vertices like this.
Yeah, so it would be kind of cool to compare what the permutation was to the coordinates that it lives on. And we could do that maybe for a project later on. Might be interesting to see if we could see the connection. But for now, what I want to talk about is what happens when we slice this. So when we slice it as it's oriented like this with the square on the bottom slice, what do we see? If we slice it just in the XY plane.
We've got four vertices on the bottom, so you'd see 4 vertices first.
And you'd see more than that, more than just the 4.
I mean,
What do you see? If I just took that slice in the XY plane, what shape do I see?
you'd see the square.
See a square. And we also see that there's some connections this time between the points. Last time we only had 1 point, so it wasn't able to be connected to anything. Here we see a square on the bottom and some points that are connected. Now if we go up a level, up 1 level, what do we see?
Well, it's another 4 arranged in a bigger square.
But they're not
connected.
They're not connected in the way it was before, but they do extend down to the bottom layer.
Right, we don't see that extension when we do the slice.
So you just see 4 distinct vertices.
We see 4 distinct unconnected vertices. Now if I go up to this layer, what do I see?
So we see 6 connected in pairs.
Well, no, we've got 8.
Or, oh yeah, 8 connected in pairs.
So you've got
So it's around there.
4 groups of 2 vertices connected by 1 line.
Okay, so we have not an octagon.
Yeah.
It's not an octagon, but it is 8 vertices connected in pairs of 2. So I've got 4, 4, 8. Going up another level?
Here you have 4 distinct vertices again.
Okay.
And then going again, you'll see the 4 arranged in a square.
On top and they're connected. Okay, would that slicing help us understand what this shape is?
Well, it might. We can definitely see symmetry, like with the hexagon. You can see there's twofold symmetry in the shape, because the pattern is sort of symmetrical. 4, 4, and then 8 is the middle layer, and then 4 and 4.
Okay. What do you think? How does this help us see the shape?
Well, it helps you see the vertices, but it doesn't help you see how the different layers connect to each other.
Right. So here,
Which is kind of a big part of it.
yeah. So what's an obvious feature of this shape that we miss by that slicing?
Well, you can't see how this layer connects to this layer, or how this layer connects up to here.
Okay.
Kind of almost-
We miss the connections in
You can't
between the layers.
see any faces on them. You can't, except for the bottom square and the top square. You can't see any of the other faces. You can't see the hexagons or the other squares.
Right. So we miss some hexagons for sure.
You wouldn't really be able to tell what those were.
Yeah. And instead, if we did it this way, when we did the slices, what would the slices be here on the layers?
So it'd be
6,
6
again, and then 6,
Six.
and another 6.
Yeah.
And then from top and bottom, they're connected in a hexagon, and then here there's 3 groups of 2 that are connected by 1.
Okay. Yeah. So that helps us see it in a different way.
Mhm.
So what we're going to do next, is we're going to look at the 5-dimensional permutahedron projected down into 4 dimensions, and now we're going to have to look at fixed 3-dimensional slices of it.
Alright.
And we're going to see if that tells us anything about what the shape is. Okay?
Alright.
Okay.